Hi everyone. Today we're going to talk about the idea of creating a three-dimensional solid by using cross sections. So we'll get to the cross sections part in a bit, but first I want to take you back to when you were a kid. Do you remember looking at pop-up books, right? So you have you open a page in your pop-up book, right? And then maybe you pull a tab or something, kind of like down here, right? And then whoa, all of a sudden a whole picture or part of something would pop up or fold up into the three-dimensional space, right? The book is open flat. That kind of represents a two-dimensional plane, but then all of a sudden, right, you got Anna, Elsa, and Olaf, and whatever these guys' names are. I fell asleep during Frozen, I'm sorry to admit. But all of these guys pop up, right, out of that two-dimensional plane, kind of into the third dimension, right? And so that's kind of the basis of what we're talking about today, right? So what we're talking about today is looking at two-dimensional graphs, right? Like y equals x squared, for example, okay? And then, right, again, those are on a two-dimensional plane, right? And then popping up all throughout the graph is some two-dimensional shape, right? But if it's perpendicular, right, to the plane, okay, right? So again, the plane here is this piece of paper, right? It's flat on the ground, right? And then all of a sudden you have all of these semicircles standing up, right? And the semicircles, right, are between the curve and your x-axis, right? And you kind of have like a set domain here, right? So in this picture, we're like starting at the origin and we're going to, some x value, right? Is that saying 97, right? Something like that. Okay. So it doesn't matter what x value we go till, right? But you have all of these shapes that are popping up. And if you kind of put them all together, you kind of get a three-dimensional solid, right? Where again, the base is based on the area, right, under x squared, right, and between that and the x-axis, okay? So that's kind of the concept here, right? So looking at this for another graph, I like this one, kind of gives you a different perspective on it, right? So like e to the x is kind of like in the back, right? So we can't see the graph because the shapes that are popping up here are covering it. And speaking of the shapes, right, going back to this picture, right, those shapes can be kind of any geometric shape you want. So in this green one, right, these are semicircles popping up from x squared, right? These are rectangles where maybe the height of the rectangle is like half of the length of the base, something like that, right? And this yellow one, right, kind of looks like maybe some type of triangle, maybe a right triangle, I'm not sure. And then this purple one, right, maybe these are squares that are popping up, okay? Right, so in this one, back to the e to the x, right, we can say these are squares as well, right, popping up between, this could be like x is equal to 1 to like, who knows, x is equal to 100 or x is equal to 7, right? And so again, we can create a three-dimensional figure, right, by having infinitely many of these shapes popping up in our domain. And so what we're going to calculate is the volume of this three-dimensional solid. And so the way we calculate the volume, right, I think of this as kind of like having like a loaf of bread. Okay, so basically what we're going to do is we're going to cut our solid into slices, right? And now, these slices all have like a fixed width, right? But if we can make the slices infinitely thinner, right, we can just take the area that we create, right, and then the width is going to get infinitely smaller, right? So we'll have infinitely many slices that we can add up the areas of, right? Add them all together, and that's how we get the volume of the solids we're going to create. Okay, so that was a lot of setup, a lot of pictures here. Let's go ahead and see this in action. Okay, so to our notes, example 1, consider the solid whose cross sections perpendicular to the x-axis are equilateral triangles. So the thing with these questions is you're going to always be told what is the shape, okay, right? What are the geometric shapes that are popping up out of your graph, right? And so it tells us cross sections, right? So those are the slices, right? So each slice is in the shape of an equilateral triangle, and perpendicular to the x-axis is good, right? So we can do everything in terms of x, and you'll see this on our picture. The base of the solid is bounded by, this is the part that can change, right? What is creating the base? What curve, what equation, right? What function, in this case, not a function, right, is bounding the base. So x squared plus y squared equals 4. Hopefully we remember that's a circle, okay? And so we're looking at a shape that's something like this. All right, so x squared plus y squared equals 4 is a circle with a radius of 2. All right, and now the way we can think about this is that at any x value, so looking at my picture here, let's say that right there is my x value. Okay, at this x value, right, I'm going to have this equilateral triangle, right, pop up into the third dimension, right? I drew my circle on a two-dimensional plane, x-axis, y-axis, but now all of a sudden, right, this equilateral triangle is popping up, okay? So what we're going to do is we're going to try to figure out what is the length of one side of this equilateral triangle, okay? Now, what's good to remember here, right, is this is a circle, right? We have the equation x squared plus y squared equals 4. Real quick, I'm going to go ahead and rewrite this as y squared equals 4 minus x squared. And then I can solve for y, and I get y equals plus or minus root 4 minus x squared. And we've talked about semicircles in the past, right? The plus or minus gives us the top half of the semicircle and the bottom half of the semicircle, okay? And so here's how I'm going to look at this now, right? Back to my two-dimensional plane, right? This point right here on the circle is specifically x comma root 4 minus x squared, right? And that is just x comma y, right? So the y there, again, I just get by plugging into the equation, that's the root 4 minus x squared, right? And so here's the thing, right? This is a circle, this is symmetric. And so if this distance right here is root 4 minus x squared, that's going to be exactly half of that length of the side of the triangle, right? And so what is the length of one side of the equilateral triangle at any given x value, right? Well, I'm just going to go ahead and double, and so it will be 2 root 4 minus x squared. Okay, and so now part B, find a formula for the area A of x of the cross section of the solid. So again, the cross section of the solid, right, we were told is equilateral triangles. And so now we have to go back into the deep recesses of our mind, right, and remember geometry. What is the area of an equilateral triangle formula? It is side length squared times square root of 3 over 4. Okay, and so what we can do with this, right, is we can take our formula for the length of the side of any one of our equilateral triangles at any given x value and just plug it in. And that is how we can get the area as a function of x. So the area, right, in terms of x, right, we can just go ahead and plug in our side length. So 2 root 4 minus x squared. That whole quantity is squared times square root of 3 over 4. And now we can just go ahead and simplify, and something very lovely will happen here, right? The 2 squared, right, will become a 4, and that will cancel with the 4 in the denominator. And so we will just get that the area of the triangle in terms of whatever x value I picked is just going to be the square root of 3 times the quantity 4 minus x squared. Now, you could go ahead and distribute this, right? I'm not going to on this one. I'll show you how to handle this in the next step, okay? One thing to note, just going back to the picture real quick, right, is x has to be within a specific domain, right? And this is coming from whatever equation we are given, right? So x squared plus y squared equals 4, circle with a radius of 2, right? And so I can only go out to x equals 2, and I can only go to the left, right? That would be x equals negative 2, okay? And very conveniently, that brings us to part C. Find the volume of the solid, right? So how are we going to find the volume, right? We're going to go ahead and add up the area of every triangle that we can make from negative 2 to 2, right? And so, right, integrate from negative 2 to 2, right? My area of my equilateral triangle formula, root 3 times quantity 4 minus x squared. Okay, and so the way I'm going to deal with the root 3 is I'm just going to put it outside the integral. So, we could have distributed. That would have been totally fine, right? I chose to just kind of leave it separated, all right? So I'm just going to leave the root 3 out, and I'll just multiply by root 3 at the end, okay? So 4 minus x squared, right? We talked about area the last couple of days, right? Area between curves. The antiderivatives on these questions aren't the craziest. Although you will see a tougher example at the end of this note sheet, okay? So we get 4x minus 1/3 x cubed from negative 2 to 2, right? So let's go ahead and plug in our values. So again, I'm just going to leave the root 3 out of this. So let's plug in 2. 4 times 2 is 8, minus 1/3 of 2 cubed, and so that would be minus 8/3. Okay, now you could simplify this, right? You could turn that 8 into something over 3 and combine, but let's hold off a sec, okay? Let's plug the negative 2 in. Remember, we have to subtract when doing fundamental theorem of calculus, right? So there's my minus there, okay? Plug in negative 2, right? I'm going to get negative 8, right? Plug in negative 2, I get minus 1/3 of negative 2 cubed, so that's 4 negatives there. So that'll become a plus 8/3, right? But there's a minus that has to distribute into each of those, right? And so that will end up actually giving me a plus 8 and another minus 8/3. So this all combines very nicely into 16 minus 16/3. And now I'm going to go ahead and put everything over 3. And so we get 48 minus 16 all over 3. And so we are going to go ahead and combine all of that, multiply by root 3, and we get 32 root 3 over 3. Okay, let's keep going. Example 2, same idea. Cross-section of the solid, consider the solid whose cross-sections perpendicular to the x-axis are squares with the base of the solid bounded by the parabola x equals y squared. And this time we're given a specific domain, 0 to 9, okay, inclusive. So first thing I'm going to do, right, x equals y squared, you graphed these back in Algebra 2. You may not recall. These are sideways parabolas, right? Another way of thinking about it is just to rewrite this is y equals plus or minus root x, okay? And so this is just a square root graph that's positive and a square root graph that's negative, okay? So again, if I choose to specify one specific x value, and you'll notice I'm kind of picking an x value just towards the end of this picture just so that we can label some things, right? At this specific x value, what is that ordered pair, right? Right there, it would be x comma the square root of x. And so this length right here is exactly root x, which is just the y coordinate there, right? And now, because I know in this question the cross sections are squares, right, I can go ahead and double that, right? And that length is also root x. And this tells me that the side length of any one square is going to be 2 root x, right? And so then the area of any one square, right, in terms of x, is just quantity 2 root x squared, which gives me just 4x as the area of any one of these squares. All right. And so for part B, this one's pretty straightforward. Find the volume of the solid, right? So we're just going to go ahead and integrate. We were given a domain here of 0 to 9, right? Of the area of any one square, which is 4x, right? And so again, antiderivative is pretty straightforward here, right? Just some power rule. We get 2x squared. Plugging in 0 into this is nice. We're just going to get 0, so we can ignore that, right? 2 times 9 squared, so 2 times 81 is going to give us an answer of 162. So that one's a lot simpler. And, you know, the more of these you see, the more you'll get the hang of it. You know, these first two examples, and actually our last example as well, right? We're looking at a base where it has a lot of symmetry, right? It doesn't have to always be that way, okay? So that's something to keep in mind as you're going through your homework, right? Don't just assume that the base is going to be nice and symmetric, right? You know, above and below your x-axis like these two examples have been so far, okay? Okay, so example 3, though, will be another one with some symmetry. All right, so let's take a look at that one. Okay, so example 3, consider the solid whose cross-sections perpendicular to the x-axis are semicircles. Now, real quick, just to go to the geometry review, what is the area of a semicircle formula, right? So circle, you probably remember pi r squared. Semicircle, right, means we're going to need half of that. Okay, so 1/2 pi r squared. All right, so that's something you can do, right, before you even consider the base or your domain or anything else, right? You're always going to be told what the cross-section shape is, okay? So the base of the solid here, right, is bounded by, again, very symmetric curves, sine of 2x plus 2, and its exact opposite, negative sine of 2x minus 2, right? And this is from 0 to 2 pi. Okay, so if I'm taking a look at this, right? So again, I'm just going to pick something at the end here, right? I'm going to pick that as my x value. Okay, and so this time around, though, right, if I'm looking at any one ordered pair, so that point right there is going to be x comma sine of 2x plus 2. Sorry, my writing's a little smushed there. Let me fix that a little bit. There we go. Okay. But here's the thing, though, right? Because of my shape, right, I actually don't want this entire length, right? Yes, this is what my base is, right? This is bounded by the two parts of my base, right? But remember, my shape here is semicircle, right? So what is that length going to be for a semicircle? That's the diameter, right? I actually don't want the diameter, right? I want the radius because that is my formula for the area. So that is going to be, right, just the top half. Now, technically, you could pick the bottom half, right? But then you would have a negative length for the radius, right? You could pick the bottom here and say, oh, negative sine of 2x minus 2. But you don't want a negative radius, right? You want the radius to be positive. So just focus on the top half here, right? Sine of 2x plus 2 is my radius, okay? And so if I go ahead and plug that into my area formula, right, I will get 1/2 pi times the quantity sine of 2x plus 2 squared. Okay, so this one is going to lead us to our trickiest integral. So let's go ahead and set this up, right? So my volume is going to be integral 0 to 2 pi of 1/2 pi times the quantity sine of 2x plus 2 squared dx. So the first thing I'm going to do is I'm just going to go ahead and take this 1/2 pi, right? And I'm just going to bring it out of the integral. And now, unfortunately, there's no good way of doing the antiderivative of sine of 2x plus 2, that quantity squared, okay? So we're going to have to FOIL this out. So I'm going to go ahead and rewrite this. This is going to be pi over 2, right? So again, I just took that out, times the integral 0 to 2 pi. And now if I FOILed out the first part correctly, I should get sine of 2x squared plus, remember in the middle, it's 2 of the product of the two terms. So 2 times sine of 2x times 2 is how I get 4 sine of 2x. And then 2 squared is 4. All of that dx. Okay. And now, foiling it out, even with this, there's no great way of doing this. You have to do 3 antiderivatives. Okay, now I'm going to go ahead and separate this into 3 integrals. Most of you probably doing this would not rewrite all of this as 3 separate integrals, but I am, just to kind of organize my work in a little nicer fashion. Okay, so let me just kind of show you what that's going to look like, right? So let me keep my equal signs purple here. And now I'm going to break this up and I'm going to color code because that's just how I do this, right? So the sine of 2x squared, that integral will be in blue, okay? And we'll keep the pluses in purple here as well, okay? The middle part, right, the 4 sine of x dx, right, we'll make that red. Okay, and the last part of this, right, is just the antiderivative of 4. So you're probably done with that before I'm even done talking, which is nice. Okay, and so you're going to go ahead and do these 3 integrals. Okay, now notice, right, because I split this up, I had to put pi over 2 in front of each one of those integrals. Okay, so I think I'm going to stop it right here. I'm going to give you a second to go ahead and try all of this. So this is it for the lesson, right? I'm going to stop talking. And so if you want to go ahead and pause right here, you can, right? So once I'm done talking, all I'm going to do is reveal the work and the answers, okay? So that's it for me, all right? I will see you next time. And now here is the correct work and answers for this integral.